Welcome to Outbreak Brief, the podcast that takes you inside the world's most dangerous infections.
And today we're looking at something that, honestly, it might just ruin your next trip to the grocery store.
Yeah, we are taking a deep dive into a microscopic menace that basically hides in plain sight. It's a pathogen that takes something as healthy and, innocent as a fresh summer salad and turns it into a vehicle for just a relentless, exhausting illness.
Right, because if you've ever felt completely secure just rinsing your fruits and vegetables under the kitchen tap, well, this deep dive is going to fundamentally change how you look at your produce drawer.
Exactly. I mean, we often assume that modern sanitation and our fancy chemical treatments have basically conquered nature's microscopic threats, right?
We do. We really rely on that false sense of security. But the pathogen we are examining today, it actually actively exploits the blind spots in those exact modern systems.
And to understand just how profound those blind spots are, we need to travel back to 1994.
Right, the Nepal incident.
Yeah, the setting is Nepal, and there's a detachment of foreign soldiers stationed there, and they are operating under strict by-the-book health protocols. I mean, these guys are not taking any chances.
Absolutely. They're highly disciplined.
Right, so they're drinking local water, but only after treating it really heavily with chlorine. And in the world of field sanitation, I mean, chemical chlorination is basically the gold standard.
It is. It's supposed to oxidize and destroy pretty much any biological threat. It renders the water perfectly safe.
Exactly. But then, without warning, almost the entire detachment is just struck down by this violent, explosive intestinal illness.
And we have to remember, these were incredibly fit, healthy individuals. This was not, a mild case of traveler's stomach that just resolves in a day or two.
Right. They were essentially incapacitated.
Yeah, it was severe, it was debilitating, and it completely bypassed their primary line of defense. Because, as it turned out, the chlorine did absolutely nothing.
It failed completely. So the culprit turned out to be a microscopic entity that essentially laughs at our standard chemical disinfectants. Which brings me to the big question. Okay, let's unpack this. How does a biological organism manage to survive the very chemicals we have engineered specifically to destroy it?
Well, the answer lies in the unique architecture of the villain itself. We're talking about Cyclospora cayetanensis.
Cyclospora cayetanensis.
Exactly. And biologically, it is a single-celled, obligate intracellular coccidian protozoan parasite.
Okay, wait, let's break that medical terminology down a bit because obligate intracellular is the key phrase there, right?
It is. It absolutely is.
Because that means this organism is essentially homeless and helpless on its own. It absolutely must breach and hijack the inside of a living host cell just to survive and multiply?
Right. It can't replicate in a puddle or on a counter. It needs a host. And the coccidian classification, well, that refers to its specific parasitic life cycle.
Like how it actually attacks the body.
Yeah, exactly. It burrows into the cellular lining of your intestinal tract, and it hijacks the host's machinery to replicate, eventually destroying the cell from the inside out.
Just totally blowing it up.
Pretty much. But the reason it survived the chlorine in Nepal, that comes down to how it travels between hosts. So, when an infected human sheds the parasite in their feces, it exits in this dormant form called an oocyst.
An oocyst. And these oocysts are tiny, right? Like about 8-10 micrometers in diameter.
Extremely tiny.
So to put that in perspective for you listening, they are totally invisible to the naked eye. But despite being that small, they carry this incredibly dense, cross-linked, two-layered cellular wall.
Yeah, and what's fascinating here is that double-layered wall is just an evolutionary marvel of environmental hardiness. Because chemical disinfectants, like chlorine, they operate by oxidation.
Meaning they, chemically burn things.
Sort of. They basically try to steal electrons to tear cellular structures apart. But the oocyst shell is so robust and chemically inert that the chlorine literally just bounces off. Yeah, it acts like a biological Faraday cage. It just repels the chemical attack.
Which is terrifying. But it also gives the parasite this built-in disguise, making it notoriously difficult for standard lab tests to even detect. But, and I love this detail, it has one fascinating quirk.
The autofluorescence.
Yes. If you put these oocysts under an ultraviolet light, like against a black background, they autofluoresce. They glow this eerie neon blue or green.
It's really striking to see under a microscope.
Right. So it's essentially a biological sleeper agent, just hiding perfectly in plain sight until someone hits it with a black light.
And the medical community really woke up to this sleeper agent after that 1994 Nepal outbreak. But here's the thing. Because it happened through a drinking water supply, the immediate assumption was that Cyclospora was primarily a waterborne threat.
Like cholera or Giardia.
Exactly. That was the working theory.
But the timeline of the outbreaks completely upended that assumption, didn't it? Because just a year later, in 1995, we saw the first documented U.S. outbreak.
Right in a hospital, actually.
Yeah, and initially, investigators suspected a hospital PAP water supply was the source, right? Sticking with the Nepal theory. But as epidemiologists dug deeper into the data, they realized the water was just a red herring. The actual vehicle was the food in the cafeteria.
Yeah, the epidemiological data started pointing entirely toward fresh produce. And as investigators tracked subsequent outbreaks through the late 90s and early 2000s, this very distinct pattern emerged. Water just wasn't the primary vector in non-endemic regions.
It was imported agriculture.
Exactly.
Here's where it gets really interesting, though. Humans are the only known host for Cyclospora cayetanensis, right? Like there isn't some animal reservoir out in the wild carrying this specific species.
That is correct. Humans are the exclusive host. So if this specific parasite is present, it absolutely means human feces was introduced into the environment at some point.
Which is super gross, but also really illuminating. So if humans are the only host, and the parasite is showing up on fresh produce, that implies a massive agricultural contamination issue.
Huge one.
Because, looking at the historical data, the major vectors are actually incredibly specific. Outbreaks have been heavily linked to basil, which accounts for like 34% of cases, raspberries at 31%, and then followed by things like cilantro, lettuce, and snow peas.
Yeah, and you have to realize the pathogen didn't change its behavior. Our global food supply chain is what evolved.
Oh, I see.
Yeah, in the 1990s, we began importing just massive quantities of fresh, very delicate produce from tropical and subtropical regions.
Where this parasite is already highly endemic.
Exactly. And these crops, things like raspberries and basil, they require extensive irrigation and manual harvesting. That brings the produce into direct contact with potentially contaminated soil and agricultural water.
Okay, so let's look at the actual transmission mechanics here, because there is a massive biological quirk to how this spreads. Let's say a farm worker is actively infected, right, and then accidentally contaminate a raspberry in the field. If I come along and eat that exact raspberry 5 minutes later, I'm not actually going to get sick, right?
You would be completely fine.
Wait, really? Completely fine?
Totally fine. And the reason is, when those oocysts are first shed in human feces, they are in what we call an unsporulated state.
Unsporulated, meaning they aren't fully baked yet.
That's a good way to put it. In that fresh state, they are biologically inert to another human. Cyclospora literally cannot spread directly from person to person.
So if my kid has it, I can't catch it from changing their diaper.
Nope, not directly.
Wow, so it's like a delayed fuse bomb. You can't catch it directly from a sick person. The environment itself has to arm it before it can actually hurt you.
That is the perfect analogy. The environment acts as the incubator. That unsporulated oocyst requires a maturation period.
How long are we talking?
Usually about 1 to 2 weeks sitting in soil or water. That's what it takes to sporulate and actually become infectious. And it is incredibly demanding about the conditions for this process.
It's picky.
Very. It requires temperatures ideally between 23 and 32 degrees Celsius, which is roughly 73 to 90 degrees Fahrenheit.
Which perfectly aligns with the tropical and subtropical regions where it thrives naturally.
Exactly. And once it sporulates in that warm environment, it is fully armed. It can survive for months in water. But despite that heavy biological armor we talked about, it does have a fatal flaw.
Oh.
It is highly sensitive to desiccation.
Desiccation, meaning if it dries out, it dies.
Yes. That formidable double wall relies on a constant layer of moisture to maintain its structural integrity, its osmotic pressure. If the environment dries out completely, the internal pressure causes the wall to literally rupture.
Like a balloon popping.
Exactly. It collapses in just 15 minutes, killing the parasite.
Wow. But if it stays moist like, say, in the damp soil of a basil farm or the irrigation runoff of a raspberry field, it just waits.
It just waits.
And that 1 to 2 week environmental delay, I mean, that has to make tracking these outbreaks an absolute nightmare for public health officials. Because by the time someone eats a contaminated salad, gets sick, finally goes to the doctor and gets a diagnosis, the farm where that produce was grown weeks ago has completely moved on to a new harvest cycle.
Oh, it creates a massive temporal disconnect. It's incredibly frustrating for epidemiologists. We are constantly investigating the ghost of an outbreak rather than the active source.
Right. And with the parasite lurking in these warm, moist environments, the people who are constantly exposed to it, they must face a vastly different reality than we do here in the U.S.
They absolutely do. In those endemic regions, the highest infection rates are overwhelmingly seen in children under 5 years old.
Which makes sense because kids are, they're interacting intimately with their environment, they're playing in the dirt, they're drinking local water, and so they're constantly encountering these unsporulated and sporulated oocysts. But if kids in endemic areas are getting hit the hardest, do they eventually build up a tolerance, or are they just perpetually at risk of this explosive illness? Because you would think that level of constant exposure would mean the entire population is just constantly violently ill.
Well, you would think so, but they aren't. The immune system is remarkably adaptive. But we really have to define what immunity actually means in this specific context.
Okay, how so?
In endemic settings, researchers observe that early and persistent exposure decreases the likelihood of symptomatic disease over time. So, with each subsequent infection, the severe diarrheal symptoms diminish.
Oh, so they develop immunity to the disease like the physical symptoms,
Yeah.
but not to the actual infection itself. Like they are still actively carrying and shedding the parasite.
That is the critical distinction, yes. These asymptomatic children act as silent reservoirs.
Wow.
Yeah, they're shedding oocysts into the environment all the time without showing any signs of illness. But when an international traveler or a consumer in a non-endemic area like the U.S. ingests that exact same parasite,
Their naive immune system just goes into total meltdown.
completely unprepared, it's devastating.
And the risk profile gets significantly darker for immunocompromised individuals, right?
Yeah.
Because for someone with a healthy immune system, this infection is miserable. But for patients with HIV, particularly those with HIV and tuberculosis co-infections, the consequences are severe.
They are life-threatening, honestly. Because clearing an intracellular parasite requires a highly coordinated cellular immune response. Your body's T cells have to actually identify and destroy your own infected intestinal cells to stop the parasite from replicating.
Right, scorching the earth to stop the invader.
Exactly. But when a patient's cellular immunity is compromised, like in advanced HIV, that defense mechanism is just absent. The parasite reproduces unchecked, causing profound intestinal injury, incredibly high reoccurrence rates, and relentless, dangerous diarrhea.
Let's walk through what actually happens when someone with a naive immune system, just an average person, ingests an armed sporulated oocyst. So you eat the contaminated cilantro, the clock starts, but you don't actually feel anything for a while, do you?
No, you feel perfectly fine at first. The incubation period averages about 1 week, though it can range from 2 to 14 days.
Okay.
And during this silent window, the oocyst is navigating down to your small intestine. The specific chemical environment of your gut actually signals the oocyst to break open. The parasites emerge, they invade the epithelial cells lining your bowel, and they begin to rapidly multiply.
So they are actively destroying the cellular lining, the villi, which are responsible for absorbing water and nutrients in your gut. And I'm guessing when the bowel can no longer absorb water, that's when the clinical symptoms begin.
That's exactly when it hits. It presents as frequent, watery, and sometimes explosively violent diarrhea. The fluid loss is just staggering.
I can imagine.
And this is usually accompanied by profound fatigue, severe abdominal cramping, bloating, nausea, and anorexia, meaning a total loss of appetite that leads to really rapid weight loss.
Just a miserable cascade of symptoms.
Yeah, patients often experience a low-grade fever and deep body aches, too.
What really strikes me from reading the medical literature is the psychological toll of this. Because this isn't a linear illness where you slowly get better every day, right? It has this weird remitting relapsing course.
It is incredibly deceptive. If left untreated, the symptoms can drag on for over a month.
Over a month.
Over a month. A patient might suffer a few days of terrible diarrhea, and then it abruptly stops. They think, oh, my immune system is won, it's over.
Right, they go back to work, maybe they eat a normal meal.
And then, without warning, the symptoms just roar back just as violently. The parasite basically retreats into the cells, regroups, and launches another wave of infection. It just wears people down to the bone.
So what does this all mean for treatment? When a patient is trapped in that exhausting cycle, what can a doctor actually do to stop it?
The primary treatment is a highly specific antibiotic combination called trimethoprim sulfamethoxazole, widely known as TMP-SMX, or by brand names like Bactrim or Septro.
Okay, so there is an antibiotic.
Yes, it works by disrupting the parasite's ability to synthesize folic acid, which basically halts its replication.
But there is a massive catch there, right? because TMPSMX is a sulfa-based drug, and sulfa allergies are incredibly common.
Very common.
So if a patient is allergic, can doctors just, prescribe a different standard antibiotic like amoxicillin or something?
Unfortunately, no. Other common antibiotics simply do not work against Cyclospora
At all.
at all. For patients with sulfa allergies, physicians have to rely on off-label alternatives that are nowhere near as effective. And in those cases, the focus has to shift heavily to aggressive supportive care.
Meaning, for someone who can't take those specific antibiotics, do they basically just have to ride out a month of explosive symptoms and hope for the best?
Pretty much. We manage the profound dehydration through intense fluid and electrolyte replacement, and we just have to rely on the patient's own immune system to eventually clear the infection.
Wow. And since we don't have a vaccine, there is zero biological way to prevent this infection beforehand. Our only true defense is literally keeping the parasite out of our mouths in the first place.
Which brings the responsibility entirely back to physical prevention and global agricultural standards. Because on an individual level, public health agencies recommend washing hands meticulously and refrigerating cut produce within 2 hours.
Right, 2 hours.
Because refrigeration essentially halts that sporulation process we talked about, and normal cooking temperatures will kill the oocysts while commercial freezing inactivates them.
Okay, but realistically, people aren't boiling their raspberries or, freezing their fresh basil for a summer salad. And we've already established that the oocysts' biological armor makes it immune to chemical sanitizers. So soaking your produce in a bleach solution or one of those commercial veggie washes is completely useless against Cyclospora, right?
It is entirely ineffective. Furthermore, the physical structure of something like a raspberry makes washing nearly impossible anyway. Think about it. A raspberry is composed of dozens of tiny little drupelets covered in microscopic hairs.
Yeah, it's very textured.
Right, so an 8-micrometer oocyst easily wedges itself into those crevices. And it is incredibly sticky. You cannot simply rinse it away under the tap.
It's like trying to blast a grain of sand out of a shag carpet using a spray bottle. It's just not going to happen.
Exactly.
So if we can't rely on the consumer to wash it off in the kitchen, the intervention really has to happen before the produce ever reaches the grocery store.
Yes, and this is the driving force behind what we call good agricultural practices, or GAPs. Because humans are the sole reservoir, the entire agricultural industry must focus on keeping human waste completely separate from the growing environment.
That seems like a massive logistical undertaking.
It is. It means farm owners must provide strictly maintained sanitary toilet facilities and hand-washing stations for all field workers. It means rigorously testing the water used for irrigation and pesticide mixing to ensure there is zero fecal contamination.
And what about municipal water treatment? If they can't use chlorine, what do they do?
Facilities have to physically filter the water. They use microscopic meshes fine enough to trap an 8-micrometer particle. Or they have to blast the water with high-dose UV light, which basically bypasses the parasite's thick wall and destroys its DNA directly.
It's like trying to stop a tank with a water balloon when you use chlorine. It just bounces right off its shell. You literally have to physically filter it out or blast it with UV radiation.
The burden of prevention falls entirely on the infrastructure.
So let's look at how that infrastructure is holding up right now. Based on the latest surveillance data, which is from June 16th, 2026, we are right in the middle of the high-risk season.
Yes, Cyclospora infections spike annually between May 1st and August 31st, which, again, aligns perfectly with the warmer weather required for sporulation.
Right. And the current data shows 145 domestically acquired U.S. cases spread across 17 states. That's resulted in 20 hospitalizations, though fortunately 0 deaths so far. And alongside those domestic numbers, there are 45 cases linked to international travel.
Right.
The FDA and the CDC are actively investigating several clusters right now, but they haven't identified one massive multi-state outbreak linked to a single product yet. But reading between the lines of these reports, 145 cases feels like a fraction of the reality.
Oh, it is almost certainly a massive undercount.
Because people just don't go to the doctor.
Exactly. Because the initial symptoms mimic so many other gastrointestinal viruses and bacteria, many people never seek medical care. They just suffer at home for a month. And even when patients do see a doctor, diagnosing Cyclospora is a complete logistical nightmare.
Because the parasite is shed intermittently, right? Like a patient could provide a stool sample on a Tuesday that comes back completely negative, even though they are actively infected and miserable.
Yes. Physicians often have to request multiple stool samples over several days just to catch the shedding cycle. And even then, standard ova and parasite lab tests frequently miss it.
Just because it's so small.
Small and hard to stain. The laboratory has to know to use special modified acid-fast stains or to utilize that UV autofluorescence technique we discussed earlier.
And even more alarming is that modern medicine relies so heavily on those gastrointestinal PCR panels now. You know, those advanced DNA tests that quickly scan for dozens of gut bugs at once. But Cyclospora is often entirely missing from those standard panels.
It's a huge blind spot. If the physician doesn't explicitly write test for Cyclospora on the lab order, the lab won't even look for it.
That's wild. So basically, we are fighting a 21st century global supply chain with diagnostic tools that often require manual microscopic investigation.
Exactly. The CDC and FDA are furiously working to develop and validate rapid molecular-level tools to trace these outbreaks faster. But currently, by the time we sequence the parasite's genome from a patient's sample and try to match it to a specific farm,
The contaminated crop has long since been consumed.
right, the evidence has been eaten.
So basically, we're in an ongoing arms race to build better microscopic surveillance before the next salad mix hits the shelves. It creates a terrifying reality for our food systems, because as our supply chains become increasingly interconnected, you have a microscopic parasite that takes 2 weeks to arm itself in the warm soil of a tropical farm. And during those 2 weeks, it can easily be harvested, packed, shipped, and sitting on a dinner plate thousands of miles away, long before it ever becomes dangerous.
It really is a ticking clock.
It is a biological sleeper agent packaged inside a plastic clamshell of fresh greens. And I'll leave you with this thought to mull over. As our global appetite for fresh, year-round produce only grows, are our testing systems and border screenings ever going to be fast enough to catch a microscopic sleeper agent before the timer reaches zero? Stay informed. Stay prepared. This has been Outbreak Brief.